Hi, welcome back. So we're in chapter 3. You must know the outline of matrix, eigenvalue, and eigenvectors. We have accomplished quite a lot from the vector understanding point of view, also the matrix understanding, and some property of a vector that help us later on to solve some problems for different application. Now I'm going to discuss the meaning of eigenvalue and eigenvectors. So what I'm going to do, actually, I'm going to try my best to bring things from the point where I have come to understand things on my own. So first of all, let me give you an equation. This presentation could be of any problem. So I'm not going to change much by graphing actually the two axes using the general form. Now you could see that general form helped me to see that this 12 is the outcome of some sort of a system engaging these two variables. To make that quite a bit clear, if I assume this system represents some sort of a product, maybe is equal to price. I see a fixed value of a price of 12, but the product, it happens to be there two different kind of a product. This is another way of interpreting the problem. I mean, what are these values here? 3x and 2y. X and y are the ratios of alpha 1, and this is the ratio of the alpha 2. And this 3 represent the actual fact of the indeterminate of x, and this represent the indeterminate of y. If I draw here another axis, explicitly I'm going to say, yes, this gonna represent the x, and this is gonna represent the y, meaning to say, to fill up a value of x here could be any value on this line, and to fill up a value of the y here could be any value of the y. And in this particular problem, if I would have to assume that x have a default value of 1, I will call it the I, and y have a default value, I will call it the j. Now what happened that I have decided on a value of x to be 3. In other words, imagine as I scaled this by 3 units up to this value of 3. The y has been scaled twice as much to be at the value of 2. So I have reached out to this particular value representing the point of 3 and 2. I have drawn a vector from origin of 0 and 0. This vector magnitude of it is going to be a value of 3 and 2. Let me again draw a new axis. I will say initial value, and I will say an end value. I will translate positioning change of x. The essential value of x was actually 1 and then changed to 3. Now the u vector represent the value of 1 and 3. I'm going to do the same thing for the y thing. Vector v represent now the magnitude of value of 1 and 2. Now, what is the difference of this presentation? What I want you to see that again I use vector presentation, but this time this vector representing an initial value of a change to an end value of a change in terms of 2 dimension. Previous variable was presenting the x and the y. The way that we present vector is quite a bit really, I mean, in many books, quite ambiguous. I mean, many people fail to understand the difference way, but the idea of vector is still in there. Now, all these 3 things graphed on the screen are the exact same thing. If I would like to adopt the perspective of a matrix, so basically x has changed actually from value of 1, as I have graphed here, to a value of 3, and I have seen that y has changed from value of 1 to a value of 2. I have just created a matrix to present the actual left-hand side of the equation. Right-hand side of the equation looks like actually this. Multiplied by a vector of alpha 1 and alpha 2. So the value here will be some alpha 1 plus some alpha 2. Another way to look at this alpha 1 was multiplied by this vector of 1 and 3. Scale this vector 1 and 3 plus the alpha 2 as it scaled the 1 and 2 by some value. I hope this essential presentation helps you to see how we are moving from one side to another side by using the tool of the knowledge that we know. Let's go ahead and try actually to graph this vector 1 and 3 and 1 and 2. So we got these 2 vectors. Now, according to the knowledge that we know, if I would have to sum u plus v, then we get a point of 2 and 5. This isn't what I want. What I want actually, a value to end up at 12. What is the best values that I can fix in here? Scaling u first, then scaling v, and then sum them up to lead me to the value of 12, as it's been requested in this particular problem to reach our number 12. Here is where we're going to get back to the meaning of this line. What is this line represent actually, as we have discussed many times in previous sections from different perspectives? Well, this is the graph of the line. And what I'm going to do actually, I'm going to pick a point on this line, 2 and 3. So I get this point of alpha 1, 2, and the alpha 2 is going to be 3. And I want to see what the result looks like. Alpha 1 plus alpha 2, so the both alphas will be 5, the sum of them according to what I have here. The result that is exactly equal to 12. So I have satisfied the equation by picking up these two particular alphas. I scale by this 2 and 3, applying this matrix A to this vector, and I end up with the value of 5 and 12. As if I have initial vector looks like this in a space of 2 and 3, end up like this in a space of 5 and 12. This transformation, let me say. So let's see how that happened exactly and what that looks like. So this is my vector alphas here. Now go ahead to the two vectors and apply these alpha to them. And as expected, I will get the value of 5 and 12. But what I want you to see is something else actually. The initial vector exactly like this. And then I multiplied this by a matrix A. Watch carefully what happened to it. It actually shifted by this angle, and you could see the direction of that vector still. So I'm getting back to the same line here. I'm going to pick up another point, the 3 and 1.5. The x scaled by 3 and the other one scaled by 1.5. Good. The vector A, which is values of the alpha. And when I apply the matrix A, look how much the change of that multiplication, it transformed that vector to this vector, obviously bigger than the previous one before. So I'm going to go back and I will choose upper side of the line, pick a value of maybe 1 and 4.5. Now the initial vector, you could see it was this one, but this time when I applied the matrix, it shifted again by this angle, but look at the directionality of the change. It went down there. Okay, let me choose a value in particular I am interested in, 1.6, 3.6. Now, interestingly, do you see this particular vector, the 1.6 and the 3.6, when I applied the matrix, transformation did not change direction of the vector. It has scaled that vector by some kind of a value. By how much it's scaled? Well, I got like 3.6 and 12, and I got 1.6 and 5.2. So choose one of these value and just get the difference, and I will get you by value 3.333. That is 10 over 3. I scaled this vector by 10 over 3. But when I get back here, as it turns out, choosing this vector x, which is actually the component of alpha 1, alpha 2, and I apply the matrix A into it, it does not actually change at all the direction of this vector. What it does, it actually gives you back the exact same vector, but scaled by some values. In this case, we call it lambda. And the eigenvalue, it's this much lambda that I am scaling x by. I hope now this visual presentation helps you actually to grasp the meaning of eigenvalue and eigenvectors. So next, let's go ahead and discuss a practical example where maybe the use of eigenvalue and eigenvectors can make a huge difference. First problem, and that is from a financial perspective. Well, we're talking about a stock, number of stocks that he bought and the number of stocks that he sold. What is the most likely behavior this particular customer would attain for these two actions on this particular property of a stock or whatsoever? Imagine I would have gone through the first two, maybe 100 days or so, and then I start to do analysis on B action and the S action that happened on each day. After that long of analysis, I start the day, opening the day with 100. He does not keep the 100, it seems, or 10 based on the history that we have. He's actually given up 20% of that amount that he have in a day, and buying back 15% 20% of what he sold a day before. Let's now create two categories, like say stock that he have and stock that he's selling. B can represent some sort of X and S can represent some sort of Y, if you will. What we are saying here about stock that he have, by the end of the day, as we are looking here, he is selling 20% of what he have. This is going to be 80%, that means 0.80. He's going and buying also to add to what he has 15% from the day before. And this 15 will be added to the 80. How about the one he sold out? Well, they be the complete opposite. He's selling already 20% plus what he sold the day before, 85% of the Y. Let's say, for example, 100 stock he bought and 80 stock he sold. If you apply that into this equation, you will end up with the total number of stock that he have afterwards. If you get the same exact numbers here, you'll get the total number of stock that he sold. The question is, what is the number we are looking at? Are we looking at a specific number? Well, this number can change. I mean, you could say, well, he started it with 20 and 100, maybe 110. And as you can see, we don't have here equal to anything yet. Now, let's transfer this into a matrix form and try to make things quite a bit clear. That we're going to multiply this by some alpha 1 and alpha 2, represent the real indeterminate of X and Y, I mean number of stocks in other ways. And that's going to equal to some sort of value 1 and value 2, I will say that way. The question is, which alpha we're going to choose? Because we don't have specific value to go for, we don't have a specific range. I have created a short code using Python, get an input, choose numbers, random numbers, and decide after maybe 50 days what the result would look like. So basically it's a simple code, a few lines. First I decided the number of the days and the number of stock buying and selling. So after 50 days we started with 50 stocks he bought, 50 stock he sold. In the second day he's going to go for 48.52, 46.54. You could see the numbers going to keep changing, but something interesting is going to happen after some time where the numbers will going to be exactly the same and the system will steady and we can know the behavior of this person. That's exactly what happened here. Now try to go ahead and try and manipulate that. Maybe let's just start with, say for example, he started with 80 and maybe he's selling like 30, something like that. 48 is going to buy most likely, 62 is going to sell most likely, and the number will go on like that. This is what's going to happen after so long time. How did I capture that? Using these two portfolio behavior of equations that I constructed based on a historical data I got from the guy before. Let's go ahead and create these two vectors here. Basically, I'm going to create a point that represents the outcome. And we're going to say U plus V. Let's assume now I will start here with 50 stock here, 50 stock here, and see what the number will look like afterwards. Basically, this is the vector. When I apply the matrix onto this vector, you could see that the vector shifted up towards this direction with that much angle. And I got this number, the A value number is 47.5, 52.7. And I get back to my code where I showed you using just the systematical way of writing the program. It was 50-50, and then we applied the two equation and we got 48.52. Actually, these are the numbers, the exact replica for that. In fact, I rounded here. Now, if I take the exact same number, this guy, and I change the D to be a decent new number, you go to the second value, is going to be 45.88, 54.13. Exactly similar to the values here, of course, with rounded value. And you keep doing this again and again until you will see by eyes that these become only one vector. In fact, if we take the value that we have seen here, 44 and 56, where the system have studied at these two values and actually substitute them here, you could see quite clear, starting from a vector of 50-50, ended up to this particular value of a vector W. Now, mathematically, it means this essential matrix A on day 1, and we assume the opening of our entire operation was with a 50 and 50, like portfolio of a total sum of 100. So we have assumed this essential vector, and then we've got another vector on the second day, we have taken this V1, let's call it, and then again we multiply it by A. We kept doing this, you will end up with the same vector again and again. Capture this behavior. It is as if we were taking A to a certain power multiplied by the essential vector that we're talking about. This operation is really expensive. Now here, before I lead you to the final closure of eigenvalue and eigenvector, I would like to show you the actual value of 44 and 56. Now, the ratio between 44 and 56 is 76, 78% or so. What does that tell me? That this customer with a portfolio of property stock, say, equal to 100, whatever he is buying is going to be 75 or 76% of what he is selling. This is the conclusion what we can reach out just by reading this. Now, where eigenvalue and eigenvector could come to a great help, if you actually capture eigenvalue and eigenvector of this particular matrix, you will see that the eigenvalue of this matrix, one of the eigenvalues, is equal to y, and the eigenvector is 3, 4, and y. And that's exactly what we have just found. Whatever the value of the second variable, the first one will be 75% of that. So easy. Instead of going to this entire operation by keep multiplying again and again, instead of that, we could have actually from the beginning just captured what is lambda and what is corresponding eigenvalue and eigenvectors. And when we read this, we know by now that after so long, a critical ratio, it tells me what is the behavior of this customer is going to be after that long of operation. I hope this example illustrates the essential practical idea of using eigenvalue and eigenvectors to bring out the characteristic of a certain behavior or a system. In this case, a behavior of a customer look like after long run. Next, let's take another example from a different perspective where also eigenvalue and eigenvectors could be at help. Let's imagine the scenario of a company that they are manufacturing some kind of a chemical product, A and B. The velocity of this captured throughout the formula as follows. A here is measured, for example, by liter. Product B, if you add 1 liter of B and 1 liter of A, then the total velocity of B will be 2. So let's assume that I started 5 liter of A and 5 liter of B. Turns out that the velocity of A, and this equals 7.5. The velocity of B, 10. Now, if you take the ratio, it's like, say, 10 over 3, something like that. This ratio is captured when I had a quantity of 5 and 5. Okay, let's change this quantity to be, say, for example, 3 and 3. So if we do the exact same story, again, 1.337. When I would like to take, say, for example, 3 of A and maybe 5 of B or something, some 2.4, something like that. Well, the ratio has changed. It turns out that if I stick with both of them the exact same quantity, I will get specific ratio. And if I manipulate different quantity for both of them, I will get different ratio. The company actually want the following. First of all, to change the quantity of A and B as much as they want. Always, I want to get back to ratio of 2. I could solve this problem using the knowledge that we learned about equation function. It's not going to be hard, but I want to show you how eigenvalue and eigenvectors can be at help in this time. Sometimes when you enter some value of A, this line is gonna looks like this. That means the velocity of A will overcome the velocity of B. You could see the values somewhere else, like say for example here, the velocity of B is overcome A. However, there is a sweet spot. No matter what the quantity of A is added and the quantity of B is added, you will always have range between both velocity. It's going to be just fine. This is going to be the actual eigenvector. So if I want to transfer both equation into a form of a matrix, so this is my matrix, and what I'm looking at some kind of a vector, some amount of lambda, scale down the exact same vector up. So if I would have this vector by entering 1 liter of A, 1 liter of B, the vector looks like this, and when I apply the matrix, you could see it shifted and changed its direction with that much angle. This is where we need to learn how to calculate the eigenvalue eigenvector, which is the formula is quite straightforward how to do that. So I have already done that, and I know that the eigenvector in this one of the eigenvector of 2 and 1, when I apply the matrix to it, it's scaled up with the quantity of W, as you can see here. We'll see what is the ratio of 3 and 1.5. That is going to be 2. So we have just accomplished what the company wanted us to do. So how to capture the equation line of this? Every point in this line will be the perfect combination of A and B. So we have come to the conclusion of eigenvalue and eigenvector on what we must know. Next, we're going to speak about combination and permutation. That's exactly what we're going to do next. I'll see you then.